Okay, in this section we're going to look at derivatives and integrals of vector functions. Suppose we have this vector function right here, and we want to look at the limit as t goes to pi over 2. Okay, so what we do is we look at the limit of each component function, and if the limit of each component function exists, then we say the limit exists. So the first one gets close to 1, the second one gets close to 0, and the third one gets close to pi over 2. So this limit exists, doesn't it, as t goes to pi over 2. The derivative? Well, the derivative, same story. You basically take the derivative of each component function. As long as they all exist, then we say that the derivative exists. This would be the derivative function, r prime of t. The idea, the picture here shows that this is our curve, this helix curve, right? At t equal pi over 2, you're over here. I believe the point would be 1, 0, pi over 2. So you start off at t equals 0, you're at the point 0, 1, 0, and as you move along here, the derivative is actually, the derivative vector, r prime of t, is the vector at this point that has the same slope as the tangent line does, okay? So if you wanted to find the parametric equations or the vector equation for the tangent line, all you'd have to do would be to take this vector, r prime of t, plug in pi over 2 for t, and you'd have the direction vector for the line, and then you would use the point at pi over 2, 1, 1, 0, pi over 2 for your point, and you could get the vector function for the tangent line, right? Now, there's something called the unit tangent vector, t. The unit tangent vector, what you do is you take r prime of t and you divide by the magnitude. So first of all, you have to compute the magnitude of r prime. I believe you get square root of 2, right, when you take the magnitude of r prime. So t, the unit tangent vector, would be the vector for r prime divided by the magnitude. So this would be the unit tangent vector. So again, getting back to the picture, you've got your tangent line at this point. The r prime is some vector here that gives the direction of the line. T is the vector in the direction of r prime that has length 1, okay? Alright, so like I was saying, if you wanted to find the vector function v for the tangent line at t equal pi over 2, we've got all the information that we need. We have the point. If you plug in pi over 2 into the position vector, you get this for your point. And we don't need the tangent vector. You could use the tangent vector if you want, but either t or r prime of pi over 2 would work just as well. So the parametric equations would be 1 plus 0t, 0 plus negative 1t, pi over 2 plus 1t. So this would be your vector function v for the equation of the tangent line. Let's keep on going. Now there's differentiation rules that you can look at in the book. The two most notable ones are that the product rule applies when you have a dot product of two vectors or the cross product of two vectors. The product rule works in both cases. An important theorem that's not really a theorem, but it really should be, because this comes up all the time. If a vector has constant magnitude, for example, suppose you have a point moving around a circle. That's a good example of a position vector that has constant magnitude. Then the position vector and the derivative vector will always be orthogonal. This comes up all the time, as long as the magnitude is constant. Why is that true? Well, here's the proof. This is a property from 12.2. When you dot a vector with itself, you get the magnitude squared. That's not hard to prove. Just go ahead and look at what the dot product is. Okay, so then what we're going to do is we're going to take the derivative of r dot r, and by the product rule we just talked about, it's r prime dot r plus r dot r prime. But isn't if this is a constant, if r has constant magnitude, then isn't the magnitude squared gonna be c squared? So the derivative, which is also r dot r, so the derivative of the left side equals the derivative of the right side. Well, the derivative of the right side is just the derivative of c squared, which is 0, right? So we know that if you add these, if you combine these two, you get 2r prime dot r equals 0, which means r prime dot r is 0, which means they have to be orthogonal. Nice, huh? All right, let's go back to looking at the lines of intersection. Actually, no. This is what I want to find here is the vector equation for the tangent line to the curve of the intersections of these two cylinders at this point. So I want to find the tangent line to the curve intersection. So first I have to find the curve of intersection. I don't think that's too hard because you have a circle here. Actually, now that I remember, this is kind of tricky. My temptation would be to let x equal 5 cosine t, y 5 sine t, but that's not going to help me because how about I handle this one? What we're going to do instead is notice that we're in the first octant, right? That we're in the first octant. So for all practical purposes, we can assume x, y, and z are positive. So if you let x be t, if x equals t, be plus or minus the square root of 25 minus t squared. Since we're in the first octant, y could be written as the positive square root, okay? Similarly, if x equals t and you solve this for z, z's plus or minus the square root of 13 minus x squared, but since we're in the first octant, z's positive, so you can just look at the positive square root. So this parameterization is valid near this point in the first octant, okay? So then what you would do, so then you'd have t square root of 25 minus t squared and square root of 13 minus t squared. That's your position vector. So what am I trying to do? I'm trying to find, so I want to find the equation, I want to find the equation for the tangent line to this vector at this point. So you take the derivative, right? Plug in the point when t equals 3. Notice, did you notice that? This is when t equals 3. Look closely. When t equals 3, x would be 3. Y, 25 minus 9 square rooted, which happens to be 4. Z is 13 minus 4, which happens to be square root of 3, which is 13 minus 4. Oh, t is 3. 13 minus 9 is 4, which is square root is 2. This is right. Anyway, so now that you plug, so this is your point, and you plug 3 in into this vector here, so you get this. So then you can find the parametric. Then you can find the vector function for the tangent line by using 3 plus 1t, comma 4 minus 3/4 t, and 2 minus 3/2 t. Pretty interesting, huh? Let's keep on going. How about this? Suppose you have these two vector functions, and the question is first find the point where the curves intersect. Again, you could think of it as parametric curves, right? How do you find where parametric curves intersect? Well, you set the coordinates equal to each other. If you set this x coordinate, t equals 3 minus s, 1 minus t equals s minus 2, and then 3 plus t squared equals s squared, you can solve this. Now, it turns out if you try to plug in 3 minus s, this is supposed to be an s. If you try to plug in 3 minus s in here and try to solve this, it doesn't work. You just get s minus 2 on both sides. But over here, if you replace t with 3 minus s and you square it, you do get rid of the t, and you end up with s equals 2. If s equals 2, then t equals 1. So the point of intersection, you could plug a t equal 1 into this, I guess, and you get 1, 0, 4. Now, another interesting question would be, what is the angle of intersection? So what that means is you want to find the equations of or you want to find the vector functions for the tangent lines, right? If you could look where the tangent lines are at that point, each of them. Actually, all you need are the direction vectors for the tangent lines. You really don't need the actual tangent line. So I want to find the direction vector for the tangent line to this vector function at this point, and the direction vector for the tangent line for the of this vector function at this point. And that's what you do. You take the derivative. In both cases, you take the derivative of the vector function like this. Then you would plug in t equal 1 here, and you get 2, negative 2, 1, negative 2, 2. Remember, this is the direction vector for the tangent line. of this curve, and then when you take the derivative and plug in s equal 2 into this one, you get negative 1, 1, 4. So this is the direction vector for the tangent line to this vector function. How do you find the angle between two vectors? You use the dot product idea. Cosine of theta is a dot. Let's call this first one a, okay? This one's a, and this one's b. So it's going to be a dot b divided by the product of the magnitude. So you get 1 times negative 1 is negative 1, negative 2 times 1 is negative 2, 2 times 4 is 8. The magnitude of this vector, I believe, is square root of 9, which is 3. The magnitude of this one is square root of 18, so it simplifies to 5 over 9 square root of 2. Find the inverse cosine, you get 67 degrees. Nice. Okay, let's look at this last example here. So we haven't talked about integration yet. We're going to do a lot of integration next section when we talk about arc length. But we would define it the same way we defined the derivative. If you look at the definite integral of a vector function, you would evaluate the definite integral at each of the components, right? And furthermore, the definite integral of a vector is going to be a vector. So we just look at the integral of each piece. First one isn't too bad. For the I vector, isn't this just going to give you an inverse tangent? The 2 factors out, so you get 2 inverse tangent from 0 to 1. So when you evaluate inverse tangent at 1, you get pi over 4 minus at 0 gives you 0. I just get pi over 2 there. The second one's pretty easy too, because notice how the top is the derivative of the bottom. So this is the form basically du over u. So when you integrate the second one from 0 to 1, you get ln of the bottom, evaluate from 0 to 1. So I get ln of 2 minus ln of 1, which is just ln of 2. The third one's kind of hard though. For the third one, you'd notice that you're going to use integration by parts, right? U is going to be ln of t plus 1, and then dv is going to be t dt. So what you end up with is this. See, u equals ln of t plus 1, and then dv would be t dt. So du becomes 1 over t plus 1 dt, and when you integrate dv, you get t squared over 2. So you get uv, look, uv gives you t squared ln t plus 1 over 2 minus the integral of v du. V du, you get minus 1/2, and you get t squared over t plus 1. Now that isn't too hard, integrating t squared over t plus 1. To do that, if you let u be the bottom, t plus 1, then du would be dt, and then the top, if t is u minus 1, then isn't this t squared, which is u minus 1 squared? So this integral isn't too terribly hard to evaluate. I'm looking at the indefinite integral, right? And then I'll put it all together. Anyways, so to finish this problem, you would then multiply the top out and divide everything by u, so it becomes this. So you get u squared over 2 minus 2u plus ln of u plus a constant. So when you go back and replace what u is, you end up with t squared, t plus 1 squared over 2 minus 2 times the quantity t plus 1 plus ln of t plus 1. Now remember, I'm evaluating that between 0 and 1. So put all that together. This last piece, I'm putting it over here, okay? I already said it was t squared ln of t plus 1 over 2 minus, now when you distribute the 1/2, look what happens here. When you multiply this by negative 1/2, doesn't that just become minus 1/4, right? So you get minus 1/4 of this. When you multiply this by negative 1/2, doesn't it cancel with a negative 2? You just get plus t plus 1. When you multiply this one by negative 1/2, you get minus 1/2 ln of t plus 1. All right, we're almost done. So we evaluate from 0 to 1. When you plug in 1, this becomes, what is this? This ln of 2 over 2? This becomes minus 4 over 4 is minus 1. This becomes 2. And when you plug in 1 here, you get minus ln of 2 over 2. So this is what you get when you plug in 1. And then when you plug in 0, this drops out. You get minus 1/4 plus 1 minus 0. Anyway, if you simplify it, the ln of 2 over 2's cancel, and I think you get 1/4. So make sure you write the answer. We're not done. The actual answer, you put those whatever you got for the integration, pi over 2 times the I vector plus ln of 2 times the j vector plus 1/4 times the k vector. And we're done. We'll see you later. Bye-bye.